So instead of doing our plug and chug approach, let's try to solve this using Mohr circle. So Mohr circle is a graphical approach. So again, you've probably heard of Mohr circle. You've probably done it before. Maybe you're very annoyed by it, but let's kind of go over it again. Hopefully we can explain it in a little bit more coherent of a fashion. So let's look at this stress tensor right here. So I want to answer the questions, what are my principal stress state? So the angle to get to that stress state, because we're not in principal stresses because shear stress here, shear stress here. This is plane stress in the 1-2 plane. What are my values of my principal stress? What about the stress state at 15 degrees clockwise rotation around the 3-axis? So basically rotating around there. And then what about my maximum shear stress and the angle to get to there? So let's go ahead. We don't want to do that, the plug and chug. You can see here's our 4 megapascals right here. And now we can see, so the Mohr circle equation was actually kind of derived from that old equation that we saw previously, which is basically Otto Mohr, German engineer in the 1800s, but saw that you could rearrange expressions for principal stress and your, basically the stress, the stress values or the stress state in an original coordinate system, and you could actually represent it in terms or in the functional form that should look familiar as a circle. So you can see here's the center of the circle, here is the radius of the circle, and actually you can plot Mohr circle for any arbitrary initial stress state as long as you're in plane stress conditions. So remember, stresses have to be contained within a single plane. 1-2, 2-3, 1-3, any of those planes. We're not working in the 3 dimensions or the 4th dimension, but anyways. So how do you actually practically utilize Mohr circle? So you draw a plot with the normal stress on the x-axis, the shear stress on the y-axis values. So remember, up here, these would be our tau values. Tau, that's our y values, and then these are our x values, our normal stresses. So remember, distinguish between normal stress and shear stress in that stress tensor. So you're going to draw a plot there. You are going to treat the stress tensor as coordinate system, so x-axis for normal stresses, y-axis for shear stresses. Plot the coordinates in the graph. You're going to have 4 coordinates that are possible, or basically 2 points, or actually 4 points, but 2 coordinates. And they're points that are going to lie on your Mohr circle. And you're going to draw a line connecting to the point. So when you're picking your line, pick your line such that the smaller normal stress value has a positive shear stress value. So you want, if in your generic plot, so tau versus sigma, you want to pick your point where the smaller value here has a positive value here. Basically, you want to be in that kind of type of coordinate, or if it's here as well. And then you want to draw the larger normal stress value with a negative value of shear. We're going to go through an example of this, but we want to draw a line like this. So you're going to determine the length of the line. That's going to determine the diameter of your circle, and thus your radius. Where the line crosses the x-axis, that's going to be the center of your Mohr circle. And determine the angle, because again, you're going to have 4 coordinates, because circular symmetry. Here, you're going to find this, and this is 2 theta. Remember, it's 2 theta due to our, again, all of our fun statics. If you see in these equations up here, everything is written in 2 theta, 2 theta, 2 theta, 2 theta. So in Mohr circle, you're operating in 2 theta space. That's distinct from your actual space state, which is just your theta value. So again, Mohr circle is not the best approach because of this 2 theta complication and some geometry considerations as well. So once you have the center, the radius, 2 theta values, you can find the principal stress state, angle, maximum shear stress value, and you can find the geometry of this. So let's actually do an example. So let's go back to our stress state, I believe, was up here. And actually, we'll go ahead and we'll follow our directions. So I'm going to basically, let's go step by step. So step 1, I'm going to zoom out here a little bit. I'm going to draw my tau. That's my y-axis. This is going to be my normal axis. So I have 15. I have 5 here. And I've got, again, 4 and -4 because of circular symmetry. So I'm going to have a point right here, a point right here, a point right here, and a point right here. So remember, these are my y values. My circle has to go through these points. And I'm going to draw my line from this low value of normal stress down to the high value right here. And this is going to be my 2 theta. So what do I need to know about my circle? So again, you see here that it's not like these, basically, this is not exactly kind of like, those values here are not points. They're points that lie on the circle, but they're not going to be exactly, your circle is not going to have the radius that just goes through here and here and here. So the radius isn't just 15 minus 5. So I need to figure out what's my center, what's my radius, and what's my 2 theta of this circle. So I have a coordinate here, I have a coordinate here. If I find the length of this line is going to be my diameter, and I could find my radius. So let's pull up our handy dandy Mathematica. We're going to do away with the plug and chug method. Instead, let's try to, let's keep this full screen here. Yeah, exactly. Actually, I want to keep the full screen. Let's keep the full screen. And let's see, hopefully, if I can pull up my Mathematica right here. Perfect. So my radius is just going to be my points, 5, 4, 15, 4 divided by 2, and that's going to be my radius. It's thinking, it's thinking, it's thinking. So I'm just picking my coordinates. So 5 and 4, here 15 and minus 4, and dividing this Euclidean distance, just the distance divided by 2, there's my radius. Where's my center? Well, I'm going to take these 2 points, I'm going to fit a function here. Here's my function. I'm going to solve when does this function equal 0, i.e. cross the axis? 10. If you remember back, it was, to that definition that we previously saw, you shouldn't memorize this, but the normal stresses, I need to add the normal stress divided by 2, that's my center. 15 plus 5, 20 divided by 2, 10, that's my center. So, with this right now, I can tell you, because again, what are we trying to find here? This right here, this is my principal stress state, lying straight on this line. Why is this the principal stress state? Because I have no shear stress values, right? My y is 0. So this is my sigma 1 value. This is my sigma 2 value. How can I figure those out? Well, that's just geometry, right? Sigma 1 is just going to be center plus my radius. Sigma 2 is going to be center minus my radius. And when I do that, I see this is my value here. This is my value here. I can also now solve and do some geometry here to figure out this 2 theta, right? Because I have, what is this value? Well, right here we know this is the center, that's 10. This is 5. So this distance here is 5. This distance here I know is 4. This is 2 theta. So I can go ahead and solve for that 2 theta value, right? So I can do, and actually we know that this is also the radius here, so I can solve that as well. So I can solve for 2 theta. So sine of 2 theta is equal to opposite over hypotenuse, 4 over radius. Hopefully I still got that. And this is my angle, 19 degrees, 19.3 degrees. That's what I have to do. I have to rotate. This is my initial stress state. I need to rotate counterclockwise 19.3 degrees. Oops, excuse me. 19.3 degrees counterclockwise to get to my principal stress state. I want to stop here and we want to remember some of these numbers. So let's actually we could let's remember this. So 16.4, let's see, there's a good way to do this. So I'm going to do a print screen right here. Let me do print screen. I want to pull up my handy dandy here. I don't think it did print screen correctly. Hopefully, yep, there you go. I want the whole thing. Actually, let me just get this. I just want this. I'm gonna paste it right here. Yep, I know. I just did it. I'm fancy. So let's go back to our plug and chug approach. Our plug and chug told us sigma 1 was, hey, 16.4. Sigma 2 was 3.596. Great. Theta, we'll come back to this maximum shear stress in a second, but look at my theta principal, 19.3 degrees. Fantastic, right? I've solved, I get the same exact answer. So let's figure out, let's go further. What will be my maximum shear stress here? Well, when my shear stress is maximized, I'm just going to be right here. What's this value of maximum shear? That's just my radius, right? My radius was what? What was my radius? 6.4. What was my maximum value of shear? Tau xy. 6.4. I'm getting the exact same answer here. So, and I could figure out this rotation, right? Like, I know that this 2 theta value here, right? So this is 2 times theta, which is at 19.3. And I know I have to rotate an additional value here. So I know that this angle in 2 theta space would be 90 minus my 2 theta, where theta is equal to, again, this 19.3. So I could figure out the rotation I have to move from my initial stress state, right, clockwise to get to that maximum shear stress state. So you might be asking yourself right now, well, Professor Steinmüller, I mean, I could figure out this 2 theta thing, right? Well, why can't I just use Mohr circle for everything? Well, what about finding the stress state that's a 15 degrees clockwise rotation around the 3-axis? So basically, I need to rotate here 30 degrees. Can you find that stress state? It'll look something like this, right? And you could do it, it's just more geometry, right? So this is where the Mohr circle, in my opinion, breaks down. There's a lot of geometry, and I'm not a geometry person, and we're not going to do geometry on this, channel unless you absolutely are dying for it or in this class. This is where Mohr circle breaks down. It's a great visual aid to check for those things: maximum shear, principal stress state, the angle to get and rotate and keep track of your rotation. But finding quickly some arbitrary stress state at some arbitrary rotation, that's where I'm going to force you all, even though all engineers should take linear algebra, but we never do because we don't have enough time to do all of that. But we are going to show you a little bit of pain, a little bit of linear algebra, to show you how to solve every single problem very, very quickly, maintain the intuitiveness of the Mohr circle approach, but allow us fast mathematical computations, and you will love this approach. I promise you, if you work on this and you kind of double check yourself, this will be the preferred approach that you'll use for every single solid mechanics problem. So we'll get to that next time. Thanks. Bye.